We now want to learn a major technique of integration, which is integration by substitution. It's really the reverse of the chain rule. So we looked at the chain rule when we did derivatives, and it was one of the most important derivative rules we learned. And so as far as integration goes, this is going to be extremely important. So thinking about the chain rule. When we take the derivative of a composition function, we take the derivative of the outside, leave the inside the same, and then multiply by the derivative of the outside. So in this case, what I have is if I integrate, which we know integration is going backwards, if I integrate f prime of g of x times g prime of x with respect to x, I should get where I started. Now let's take a closer look at that. So when you look at this integral has three functions inside of it. F prime of g of x times g prime of x. So there's three functions, f prime, g, and g prime. Ultimately, out of those three functions, we have to build this answer. So first we look at g of x. Okay. Well, if we can identify which one of these three functions is g of x, all I have to do is take it and place it there. I don't have to do anything with it. I just figure out which one is g of x and I put it right here. And once I do that, the only other thing I need to find is f. So going backwards, if this is f prime, then in order to find f, all I really have to do is integrate f prime of x and find f. And once I find f, I'll just plug g into it and that'll be my answer. So in looking at this chain rule, while there are three functions sitting here inside this integral, the only one I actually have to integrate to get the answer I want is this function right here. So if we can identify what that is, we can isolate that function and work with it. Sounds like a lot. It's probably confusing. Here's the easy way to do it. So if we say let's let u equal g of x, the derivative of u with respect to x is g prime of x. I could also take this dx and I can move it to the other side of this equation and put it here. So now it's no longer down there. And I have this. So what I'm going to do is use this substitution. This g of x here is going to be replaced with a u. So if I'm looking at this integral, I have f prime of u. And then this g prime of x dx is going to be replaced with a du. And by rewriting this integral this way, it allows you to just focus on the one function that needs to be integrated. Now, we changed the variable from x's to u's by using the substitution, but it at least makes what looks like a whole lot going on right here much simpler. Okay? We do some examples, you'll see it a lot better. Again, this is basically what I was just explaining. Instead of writing this as f prime, I write this as f, and then capital F is the antiderivative. It's really the same thing as saying this is f prime and this is f itself. It's just a different way of writing it. But the key to this is the substitution, g and g prime. When you can identify what g and g prime are, so your u and your du, that's how you can isolate this function here that then needs to have the antiderivative found for it. So how are you going to do that? Well, when you look at an integral, you're going to have to see that there are two functions inside your integral. One is the derivative of the other. So if I gave you something like this, the integral of 3x squared plus x cubed times 6x plus 1 dx. You should clearly see that this function is the derivative of this function right here. So I have a g and I have a g prime. So that means that this is my f, which is the cube, the third power. So if I say let's let u equal 3x squared plus x, then du would be 6x plus 1 dx. The integral would turn into u cubed du. This g is now my u, and this g prime dx, which is here, is du. And so now I just have this integral, which is a very simple integral. So it takes everything that's happening here, which looks a lot like a lot's going on, and simplifies it simply just to u cubed du. And the integral of u cubed is u to the 4th over 4 plus c. But that's the answer in terms of u. This was an answer, we wanted really what we had in terms of x, dx. Well, since we know u equals this, 3x squared plus x, we just write 3x squared plus x to the 4th over 4 plus c. And there's our answer. So in understanding how the chain rule worked, you get better understanding of how this substitution rule works. But it's really key is recognizing a pattern of this g and g prime, or the u and the du. Not every integral is going to have that pattern, but the ones that do, we integrate using this method of substitution. So here are a few examples. 1. If I say u equals x squared plus 1, the derivative of that would be 2x dx. So if I take this 2x and this dx out, I can replace it with a du. If I take this x squared plus 1 out, I can replace it with a u, which would turn this integral into u to the 4th du. But I had to recognize right away that the derivative of this is this, that I have a function and that function's derivative sitting right in my integral. Now that I do the integral, it's just u to the 4th, which will be u to the 5th over 5 plus c. I resubstitute the fact that u is x squared plus 1, and there's my answer. Same thing here. You got to recognize that this function's derivative is sitting right here. So if I let u equal x cubed plus 1, and I could just let it be x cubed, but I want to try and get as much of this out as possible. So I could also let it be x cubed plus 1, and now more of this function is going to be u, which makes things simpler. The derivative is 3x squared dx. Remember, that dx comes from the fact that we're really taking the derivative of u with respect to x and getting 3x squared, and I'm moving the dx over to the other side. So anyway, the integral becomes the square root of u du. Well, that's the same thing as u to the 1/2 du. If I add 1, I get u to the 3/2 times 2/3 plus c, because I have to divide by 3/2, but if I divide by 3/2, I multiply by the reciprocal. Change your u's back to x's with your substitution, and there's your answer. A lot of these examples will all look generally the same. I mean, look at this one. If u is x squared plus 1, the derivative is 2x dx. That turns this integral into u squared du, which would give me u cubed over 3 plus c. Again, just power rule at this point. Once you have this, it's just a power rule integral. And so you get x squared plus 1 cubed over 3 plus c, and there's your final answer. Now, it's not always going to work out that perfectly. Look at this next example. If I let u equal x squared plus 1, the derivative is 2x dx. I don't have a 2. Like I had here, I had the 2. I don't have that extra 2 sitting right here. There's a couple of ways you can handle that. To me, the easiest way is to do this. I have an x dx. So let me turn this into just x dx. How? Take the 2 and divide it to the other side. If I divide it to the other side, now it's gone. Now I just have an x dx. So that means x dx will come out, and a du over 2 will go in its place. So I'll get the integral of x squared plus 1 squared, would be u squared, du over 2. Now this over 2 is really a constant multiple that I can pull out as a 1/2. And now it looks very similar to this one. It's just multiplied by a half. So sometimes it's not perfect. You're missing a multiple of something. I was missing the 2 or whatever. Multiple I'm missing. You can take care of that by dividing it and pulling it out. So I end up with 1/2 times This will be u cubed over 3 plus c. The 2 and the 3 multiply and give me a 6. The u was x squared plus 1 cubed plus c. Now remember, you can always check your answer by taking the derivative of it and seeing if you get back to where you started. All right, so your steps you want to follow when we're going through this changing variables or substitution. You need to figure out what your u is going to be. And the key to doing that is recognizing there are two functions inside, one being the derivative of the other. And you know what? Sometimes you don't pick the right one. Sometimes you pick a guess and it's not the right one. So you try another one. Once you do that, you're going to compute what du is, which is the derivative of this function. Now you have your g and your g prime, or we can say your u and your du. We'll rewrite the integral in terms of u. Now we're going to actually find the results of that integral. Okay, so do the integration, which should be very simple. Most of the times right now it's going to be a power rule. Replace u with your g of x function, so now you're back to x. And you can always check your answer by taking the derivative. So here are a couple examples. So let's look at A. If I said u was 3x minus 1, the derivative is 3 dx. Here's the 3 dx. So I have the integral of u to the fourth du. Again, 3 dx is du. This is u. So I pull those things out. I'm just left with u to the fourth du, which would then give me u to the fifth over 5 plus c. Replace the u with 3x minus 1 to the fifth over 5 plus c, and I have my answer. Keep going. If I look at this one and said u was x squared plus x, the derivative is 2x plus 1. So the integral would be 2x plus 1, dx. So the 2x plus 1 dx is du. This is u, so I get u du. Since this isn't raised to anything other than 1, it's just u to the first du. Integral will be u squared over 2 plus c. So I get x squared plus x squared over 2 plus c. One more, again fairly simple. If u equals x cubed minus 2, du equals 3x squared dx. There's 3x squared dx. There's the u. I end up with the square root of u du, which would be u to the 1/2 du. Integrate that, I'm going to get u to the 3/2. If I divide by 3/2 and really multiply by 2/3 plus c, resubstitute, and we get x cubed minus 2 to the 3/2 plus c. Here are two examples. One is easier, one is harder. They look fairly similar, but really different in the way we're going to get these things kind of done. The second one has a major issue in it that we haven't dealt with yet. The first one is pretty straightforward. If I say u equals 2x minus 1, the derivative is 2 dx. Now we don't have that extra 2. If this is u, we just have a dx. We don't have the 2, but we talked about that. Just divide by the 2. And so you end up with integral of square root of u du over 2. The du over 2 really comes out as a 1/2. This is u to the 1/2 du. You integrate. You have u to the 3/2 times 2/3. We just did that problem a second ago. You have this 1/2 times 2/3 will give you 1/3. U go back to be 2x minus 1 to the 3/2 plus c. Pretty straightforward one, not really much to it. Looks a lot like all the ones we've done so far. This one's a little different. I make the same substitution, u equals 2x minus 1, and du equals 2 dx. And I'm still going to divide by 2 like I did over there because I don't have an extra 2. But if this comes out and becomes a u, this comes out and becomes a du over 2, I still have this extra x sitting here. And I can't have an integral that has x square root of u and du over 2. I can't have an integral that has x's and u's in it. So what we're going to do is we're going to get that extra x out of there. Now it doesn't look like we'll be able to do that, but we will. Look at this equation right here. I can rewrite that equation as u plus 1 divided by 2 equals x. Move the 1 over, divide by 2. And what I just found out is what x equals in terms of u. So I'm going to use that as well. So this is going to replace by a u. X is going to be replaced by a u plus 1 over 2. And dx is going to be replaced by du over 2. So what do I have? I have u plus 1 over 2 times the square root of u times du over 2. Since these are all multiplied together, the denominators will multiply and come all the way out to the front, which will give me a 1/4. I have a u plus 1 times square root of u du. Then in order to get this done, I'm going to distribute that in here. So that's going to give me 1/4 the integral u to the first times u to the 1/2, because this is u to the 1/2, will give me u to the 3/2, plus u to the 1/2 when this distributes into there, it's just times 1 du. And now I have this integral. Since these are added together, I can do each one of these integrals separately. I still have the 1/4 out of the whole thing, but this will be u to the 5/2 times 2/5 plus u to the 3/2 times 2/3 plus c. So resubstitute. I have 1/4 times 2/5 times 2x minus 1 to the 5/2 plus 2/3 times 2x minus 1 to the 3/2 plus c. This one's a little harder, and it deals with exponentials, which we just recently talked about. So sometimes you look at an integral and you don't know what to do with it. There's a lot going on with this integral. And for right now, anything that has something that's slightly complicated looking in it, most likely is going to be a u substitution, because that's all you know how to do. And so if you don't know what u should be, sometimes you just try something. You could let u equal 1 over x, you could let u equal e to the 1 over x, you could let u equal x squared. I mean, these are all different things you can let u be, and you see what happens in terms of your du. What's going to work out is if I use the first one. If I let u equal 1 over x, which is the same thing as x to the negative 1, du will be negative 1 x to the negative 2 dx, which really is the same thing as negative 1 over x squared dx. If you look at this, I have 1 over x squared. If I pull this out, it's 1 over x squared dx. Aside from the negative, I have this part right here. So all I really need to do is swap that negative over to the other side of this equation, and this whole thing here can come out and a negative du can go in its place. This is coming out and a u is going to go into its place, so what I end up getting is the negative from the du. I'll pull all the way out to the front. I'm going to have e to the u du. Well, we've already seen that the integral of e to the u du should be e to the u, or e to the x dx is e to the x, so this will be negative e to the u plus c, u being 1 over x, and there's your answer. If you're not sure that's right, take the derivative of it. So here's another one. We're not going to use substitution right away, though. We're going to use something that we've done before, and we're going to split this up into 3 separate fractions. I'm going to write this as e to the 3x over e to the 2x minus 3e to the 2x over e to the 2x plus e to the x over e to the 2x dx. And then I look at this. Well, if I'm dividing, I should subtract these exponents, which would just give me e to the x. Here, these will cancel completely and give me a 3. And here, if I subtract, I get e to the negative x. Since all these are added together, I can integrate each one of these separately. Well, e to the x dx, you don't need any type of substitution. 3 dx, you don't need any type of substitution. This one, you may look at as a substitution problem. And so if we look at e to the negative x dx, and think about how we're going to integrate that. Well, we know that the integral of e to the x is e to the x. And the integral of 3 is going to be 3x. So what's the integral of e to the negative x? Well, it's not going to be e to the negative x. It's close, but it's not it. If I let u equal negative x, du is -1 dx. And I don't have that extra -1 here. So what I'll do is I'll swap it to the other side. So now I just have 1 dx or dx. So there's my negative du. And so now I end up with this. The negative comes all the way out. And so I end up with negative e to the u, which would then give me negative e to the negative x. So to integrate that, the substitution shows you where this negative would come from. And it comes from the fact that you need that extra negative in your substitution. But that is the integral. So we use two things. One thing we've done before, which is split up the fraction. And the other thing is for this piece, we use some substitution. So here's two more. Again, a little bit higher in level of difficulty, just because it's not going to be a power function necessarily for this first one. So if you look at this, I think you can clearly see that the derivative of this is this. So looking at that, if u equaled x to the fourth plus x, du would be 4x cubed plus 1 dx, which is exactly what you have here, 4x cubed plus 1 dx, and this. But look at the resulting integral. The resulting integral would be du over u. And you got to remember how to do that. Well, that is the same thing as saying 1 over u du, whether you write it this way or this way, it doesn't matter, they're the same thing. You got to remember, and this is where you have to have your basic integration rules memorized, that that integral is the log of u integral, because of the derivative of log of u is 1 over u, or 1 over x, if it was log of x. Resubstitute, and there's your answer. Okay. This next one, pretty much the same deal. We got a little too much going on with this one, which makes it a little bit complicated, similar to one we did two back. If u equals x plus 1, the derivative is just 1 dx, but I'll have this extra x here. Well, again, we could do this. We could say that x equals u minus 1 using our substitution. And now I have this 2 here is just a constant multiple I can pull out. That x is going to be u minus 1. This will be u squared. This one right here will be u squared. And dx is just du. And so now I have something like this. I'll split this up like I did with that exponential one a second ago. And so I'll have u over u squared minus 1 over u squared du. Sorry, that should be du. Simplify this one to just 1 over u. Write this one as u to the negative 2. And then you can integrate. So I can do them separately because of the minus. I can do this one, which we just did a second ago. That's log u. Minus, this one will be u to the negative 1 divided by negative 1. This whole thing is multiplied by 2 because this whole integral was multiplied by 2. So I put parentheses around the whole thing. Resubstitute 2 times log of x plus 1. This negative and this negative here will cancel and give me plus. This being a negative 1, I can put 1 over u, again being x plus 1, plus c, and there's your answer. I say those ones are the hardest ones. When you make a substitution but there's still some extra x's left inside, they can be the most difficult one because it's hard to figure out even what u should be in the first place. And that's more of a trial and error thing, and the better you get at it, it comes with practice.